Hello, further mechanics to Edexcel people. It is indeed almost results day, A-level results day for me. This is why I'm going to show you a really cool friction trick that is not very mainstream, but I think it's a much more visual and easy way to understand and solve this certain type of further mechanics to problems in Edexcel. Alright, so for an object not moving with respect to a surface, the surface can exert a normal force N that is perpendicular to the surface and a static friction force that is parallel to the surface. Since this is static friction, the friction between two objects that's just not sliding against each other, this force can be from 0 to a maximum of mu n. Its magnitude has a maximum of this one, where mu is the coefficient of static friction and the n is the magnitude of the normal force. So the static friction force vector, you can represent it like this, like an arrow, and it is possible that it is like this, or like this, or like this, right? All of these are possible as long as the vector is parallel to the surface and the magnitude does not exceed mu n. It's getting cluttered. Let me erase some bit. So here's a visual way to represent this restriction. Okay, let's say we have object for some situation, the normal force is n. Draw a line like this, where this length here has a length of mu n. This one also have a length of mu n. The friction vector can only lie with its tail here, and its tip can only be inside this orange horizontal line that we draw, right? If it exceeds, then its magnitude is bigger than this, which is not a physical possibility. Alright. Okay, alternatively, you can also think of the vector n plus f. Hop, pop, pop. So this n plus f can only be a vector with a tail here and its tip lying on this line for a given normal vector, that is. The maximum deviation from the normal line for this n plus f total vector sum is like so. Like this is the maximum tilt that it can go with respect to the vertical, the line perpendicular to the surface. And this maximum angle is going to be, this is the right angle. So this angle, we use tangent. Tangent of this angle equals opposite over adjacent, mu n over n equal mu. So you see, right? For any normal force, the maximum tilt of the vector n plus f is mu. It doesn't matter what n it is, the maximum tilt is so that the theta is equal to arctan mu. Here's a diagrammatic way of representing this. Here we go. So here's arctan mu. So I drew two lines like so. These two angles are arctan mu, or the theta. And now vectors that can physically represent n plus f must have tails starting from here and its tips ending inside this region. If this tip is inside this region, this angle of deviation is less than theta, and therefore it is physically possible. Vectors with this tip outside of this region, the angle of deviation would be more than arctan mu, and therefore it wouldn't be a physical possibility. Let's illustrate this visual way with a problem. A car moves on a circular track of radius r. So the track is banked at an angle of theta. So here's the track. It was probably not as banked as crazy as this. Here's theta. So this is a side view of the track. The coefficient of static friction between the tire and the road is mu. Alright. What is the maximum constant speed that the car can travel around the tracks? Okay, so acceleration is v squared over r, directed towards the center. Thus the net force is mv squared over r, directed towards the center. Now, the forces on the car are gravity, let's draw the car. Here's the car. It experiences a force of gravity and also a force of normal force and friction force. Let's combine normal force and friction force into one vector sum. Now the mg plus n plus f equals the net force. We know that the net force must be horizontal and point towards the center of the circle in order for there to be circular motion around the track. So I just have to be horizontal. This mg is a fixed value, and thus this n plus f, the height must also be mg, so that the vector sum is horizontal. Let us draw this triangle thingy onto this surface. Here's the normal. here are the two lines which represent where the vector n plus f can exist in. We know that its vertical height or size must be mg. So there's sort of a restriction also in that sense, like can only be, let's say, here or here or here. Those are possible vectors n plus f. Now, the vector n plus f, such that this height being mg and the centripetal force is maximized, because we want to maximize the, let's repeat that. Now the vector force n plus f, such that we get a maximum centripetal force, is, like this, lying on this side of the slanted lines corresponding to like these. And now this angle is theta. This one's the same as this one. You can think of this as being rotated so that this becomes horizontal and this becomes the normal, and this is vertical, this is the normal. So this angle is theta here, and this angle is arctan mu. Thus, from here to here, this angle is theta plus arctan mu. Therefore, the net force using trigonometry is equal to mg tan theta plus arctan mu. That equals the centripetal force, that equals mv squared over r, and thus v, or the maximum one, will be rg tan theta plus arctan mu all square root. Now this might look a little unfamiliar, but if we expand this tan expression is equal to and if you compare it with the normal way of how you would do this for the mechanics problem, it's exactly the same expression. So yeah, this is actually quite a more geometric way of explaining how the forces due to the surface act on the car, and what kind of, or what force exactly should we have so that we maximize the maximum speed that the car can go around. Let's try another problem to illustrate how this geometric way is advantageous in solving friction problems. Okay, so the problem is we have a surface and a box of mass m. The coefficient of friction between the surfaces is still mu. Now we want to push the box, right, so that it starts moving. What is the minimum force that what is the minimum force that we can provide so that the box start moving? Now let's look at all the forces on this object again. We have the weight, we have the normal and friction force, but we'll combine it into one as usual, and we have the force that you push the box with. So 3 types of forces here. Now if your pushing force is small enough, well, obviously your box isn't going to move. Your friction will be enough to resist the motion. So since it is not accelerating, the net force on this object must be 0. Here's a vector diagram for it. All the forces should sum to 0. Now you might say, oh, the minimum force I need to push the box should be mu n. Maybe because you say, I just push this guy sideways with mu n, and then the friction force is going to be at its maximum mu n. If I push the box a little bit harder than mu n, this box will start moving because friction is not enough to counteract. Now that is not entirely correct, because this is correct if we can only push horizontally, but we can push like sideways and also upwards, so that we can reduce the normal force being the vertical height of this green vector. We can reduce that, which means that we will reduce the maximum possible friction force that can be provided by the surface. So it will take less, they'll possibly take less pushing force to start moving the box. So let us once again draw those triangle lines again. And let's consider a possible let us consider a setup like so. We push with force F. There is always a gravitational force of mg, and this green vector, normal force plus friction force, is inside this the region here. So we can actually adjust our blue force F, and then the normal and friction force will adjust also automatically to counteract our pushing force so that the box is stationary. If our F is so that it looks like this and the tail is inside, then it's very possible for the normal force and friction force to be like this, to oppose. And since this green vector is inside the region, this is a physical possibility. What if our blue vector is outside this region? Our green vector will be outside this region, but that is not physically possible. Our angle of deviation cannot be more than arctan mu. Therefore, in this case, physically actually, the normal force will still be the same height in order to prevent the box from falling into the ground. Yeah, by giving a force so that its vertical acceleration is 0, so it doesn't sink into the ground, but its friction force can only be so much. It can only be a maximum of mu n. So therefore, the net force on the box is non-zero. The box will start accelerating. This means that in order for the box to start moving, we should choose our blue force so that it has a tip right here, it has a tail outside here, but we want to minimize the length of this blue vector so that we minimize the pushing force that we provide to the box, but we'll still make it move. Now, for which endpoint now for which endpoint here will our blue vector be the smallest length? It will actually be right here, so that this is right angle, and this point is just touching this orange line. That will minimize our F while making the box move. This angle as usual is arctan mu. This is a triangle, right triangle. So we can use trigonometry. F equals mg sine arctan mu. And of course, this is mu, this is 1, this is right angle, and this is the angle. So the tan of this angle is mu. The sine of this angle is mu over this one, opposite over hypotenuse. There we go. Not only does this tell us that the minimum force we need is this, but also using some angle chasing, the force, we should push it upwards with an angle, this one. This angle should also be arctan mu. Is arctan mu above the horizontal. So that is a very interesting way, isn't it? I hope you learned something today. Take care.